Hi, everyone. Today, we'll be talking a little bit about stateful services and how we at Netflix iterate on them. My name is Joey Lynch, and I'm a senior software engineer on the cloud database engineering team at Netflix. I love every form of distributed system that you can come up with. I mostly work with databases like Cassandra, Elasticsearch, Zookeeper, and then on the side, I dabble with service meshes. And today, I would like to talk to you about four main things. So I'm going to start with a little bit about Netflix kind of cloud philosophy, how we try to approach deploying services into the AWS cloud. Then I'm going to talk about what makes stateful services particularly difficult and perhaps challenging to deploy to cloud environments. And then I'll kind of get into, in my opinion, the fun part of the talk, where we'll be talking about how do we actually solve these problems? How do we manage state in the cloud? And then I'll close with a couple of kind of like order of magnitude improvements where like little changes can make big differences in how you manage state. All right, so let's get started with the cloud philosophy. Netflix's cloud philosophy is that the AMI, the Amazon Machine Image, is the source of truth. So we don't use configuration management. We don't use many typical things that you might use as your source of truth. Instead, we use the AMI as a source of truth. And there are kind of two pieces. I know you can't read this, but the two pieces are your base AMI, which has operating system information. For example, in this case, a Cassandra AMI is based on a Xenial base image. And that comes with a bunch of kind of baked-in defaults for us. Things like enhanced networking turned on, good stuff like that, using a HVM VM type. And then on top of that, my team, the CDE team, layers on all of the pieces of software which turn this base AMI into a Cassandra image. And that's all of the things that we layer on. You might not be able to see it, but the basic idea is things like specific kernels. For example, like our databases run very recent Linux kernels because they have significantly better I/O schedulers. We might actually install like the database as well as like tooling to help us collect metrics or do state transfers. So this is really great because if the AMI is the source of truth, then you've achieved immutability. The AMI is the state of the instance. To build new code, you just build a new AMI. To deploy, I mean, you guys have all heard about Netflix's red-black ASG deploys with new AMIs. ASGs just autoscaling groups and ASGs just take care of it for you. If something fails, it spawns a new instance. And this is like unicorns and rainbows, right? It's like pretty great. Except for that when you start looking at stateful instances, they have all the things that non-stateful instances have, like code, like services, different databases, configuration. Our data stores are maybe like more heavily tuned at the OS level than stateless instances might be. We have tooling, but what else do we have on our stateful instances? Well, we have a whole lot of mutable state. And that mutable state kind of just throws that immutable AMI out the window, because the moment that you start making a certain shard of a database different from another shard, then that becomes kind of a special instance, and it's no longer based on the AMI. So I like to say that at Netflix, when we moved to a service-oriented architecture, we kind of just like threw all our state into a closet, which is the data tier. And it didn't make the problem go away. It just moved the problem from your applications to your data stores and to your stateful caching layers. And this is difficult because state is really heavy. And what I mean by that is that when instances fail or when hard drives fail, it's very difficult to move and recover the state that you had before. And just to illustrate that, I've made a little diagram here that kind of shows a couple of commonly used instances, both for on-disk storage and for in-memory storage. And this graph might be a little tricky, but on the x-axis, we've got essentially how much money that instance costs per gigabyte of memory on the instance. So this is kind of just a normalized, how much money am I spending per gigabyte of memory. And you can see that, for example, like the C5D out there is like quite expensive per gigabyte, because that's, it's meant for compute, versus like the X1E 16s, which are made for large in-memory data stores, are very cheap per gigabyte. And then the size of these circles or squares corresponds to the cost per gigabyte stored. And what I'm trying to do there is show kind of that there are certain instances like D2. So the big purple blob are D2 instances. And they are very cheap per gigabyte. You can store a lot of data on them. But there's a trade-off, and that trade-off is on the y-axis, which is how long it takes to recover the state from that instance if it fails. So this is a pretty simple calculation. It's basically just take the amount of data and divide by the network bandwidth. And you can see that a D2, if it fails, might take you a day to recover that state, compared to, for example, a C5D, where you can recover it on the order of 15 minutes. And then like your typically stateful instances, like your I2s take 6 hours, your I3s take 2 hours. And this is really what I mean by state is heavy. It's this graph. It's the idea that when you lose your instances, it takes you a while to recover the state that you've lost. And this really leads to another realization, which is that stateful services are kind of just like different trade-offs along the caches all the way down. It's caches all the way down, starting with your application. And the state that you store in your application might be in memory. It's going to be very expensive, and it's not going to be terribly durable. Like those instances die frequently. Maybe you auto-scale them up and down using auto-scaling groups. And then from your app, maybe you use some type of distributed in-memory store like EVCache, which is pictured here, essentially just memcache. And then on top of that, you then move one layer down. And again, your cost is going down, but your durability is going up. So now you've hit a data store that stores its data in drives. And then finally, of course, the source of truth for all of Netflix, if you will, is the backups in S3. Right? These are where we get our durability from. And that's also the cheapest. But there are additional trade-offs. For example, you're also trading off latency. The cheaper and the more reliable and more durable storage tends to be slower. So for example, S3 is slower than drives, than hard drives, which are slower than in memory. But they're also more reliable. So these understandings kind of help us understand what makes stateful services different from stateless ones. In addition to them having state, what that really means, though, is that every instance that accepts writes, that accepts mutations, is kind of a special snowflake, and you have to deal with it. You can't just let it die and just be like, oh, well, we'll just launch a new instance from the AMI. You have to be cognizant that your state matters. The second thing is that we've seen that that stateful instances have many components. For example, they have the different data stores, they have all those different packages, and those different things require different iteration rates. And that's going to be kind of the key for us dealing with stateful instances, is that we don't have to throw away the state for a lot of these components. So this leads me to how we're going to manage state. So now that we kind of understand the problem, we can start trying to tackle it. How do we manage state? Well, the first strategy is don't manage state. It's a really great idea. We can just use a different closet and put all of our state somewhere else. So I kind of consider Amazon GP2, EBS GP2 and IO1 to be their own kind of closets, in the sense of now your data store is stateless. The state is handled by EBS. You don't have to worry about it anymore. If your instance dies and a new one comes up, you just reattach the EBS volume. It takes a few minutes. And this is a very easy and accessible way to turn your stateful instances into stateless instances. But there are some trade-offs. And the biggest trade-off is performance. So Amazon Instant State, things like I3s. This here is a latency graph of I3 disk IOs. You can see here that I'm running a tool called BioSnoop, which allows you to inspect every single IO against the drive and see how fast it is. It's a great tool. I use it all the time. And one thing that's amazing here is that Amazon i3, as an i3 4x large, is achieving a median IO latency of 64 microseconds. That's insanely fast. And in fact, Instance Store these days, like things like NVMe Instance Store, is often not the bottleneck in our systems anymore because it's so fast. But EBS is slower. EBS GP2, which I think is a fair comparison to instance SSDs, is comparatively slow. And it's about an order of magnitude slower. So instead of 64 microseconds, we're going to be talking about 800 microseconds, which is still historically very fast. But comparatively, it is slow. And so we have to be cognizant of this when we're designing our system. So for example, we might care a lot more about our OS cache hit rates on EBS-backed instances than on ephemeral ones. Because if we start missing the OS cache, we're going to be seeing millisecond latencies instead of 60 microsecond ones. But EBS GP2 also has positives. So this is a diagram from a paper that we put out about the effect of kind of cluster size in Cassandra and the availability. And I just wanted to call out this one graph because I think that it is a very important one to understand, which is that when you use EBS and you make your stateful instances stateless, you actually get significant availability gains. And the reason for that is because when an instance fails, you don't have to wait that recovery time. Which is really kind of, if you think about it, in a replicated database where maybe you have 3 copies, if you've lost 1 copy, you're at risk, right? And so you want to minimize the risk duration. So here we can see that distributed databases like Cassandra, on the y-axis, we measure their outages as expected centuries between outages. That's pretty cool. That's something that is pretty unique to distributed databases. But we can also see that the top line, which is running with an EBS attached volume, is almost 1 or even 2 orders of magnitude more reliable than running on Instance Store. And that purely just comes down to the math of recovery time. If you're curious about the source of these analyses, I've left links in the bottom of the slides, so you can go check it out if you want to see it for yourself. So we've talked about how GP2 has trade-offs. There's another option in the strategy 0 where we don't manage the state, which is that we can use an even bigger closet. So Amazon has a number of really great database as a service options. Netflix absolutely makes use of these. Things like Aurora, things like DynamoDB, Elasticache. The state is someone else's problem. They'll pick up the pager. You don't have to. And the only real trade-off is that you have to pay them for it. And that leads me to kind of this checklist of questions for should you run your own stateful services or should you make it Amazon's problem? Well, if you need a specific data store API that Amazon doesn't provide, then perhaps you need to run your own data store. If you need to be under full control of the latency SLOs or SLAs of that system, then you're probably going to need to run your own data store. Maybe you need to meet specific regulatory requirements, have the end-to-end understanding of where your data is, that it's encrypted at all times, how it's encrypted, things like that. Number 4 is a common one for Netflix. At our scale, the budget of paying someone else to solve the problem can actually be quite significant. And this can often be a driving reason for you to run your own stateful services. And then finally, I mean, if you like enjoying debugging difficult distributed systems problems, running stateful services is a great way to do that. All right, so now that we've talked about the option, which is not to manage state, now let's talk about how we are going to manage state if we've decided we're going to. So step 1 is isolating your state. And what I mean by this is thinking about how you lay out your EC2 instances. In particular, the vast majority of the code or of the services that run on an instance are probably pretty stateless. Things like the actual database itself, the Debian package, the OS image, the system packages, background services. These things can be changed without affecting the mutable state, which is the really difficult problem. So we want to try to keep those stateless components to one side, and we want to keep the stateful components, things like the actual mutable data, maybe our log data, that to a different side. And this will come in important later when we're actually trying to move the state around. But the second thing that we have to do before we start deploying stateful services is have a really good end-to-end test system. And this really comes down to, if you're going to manage stateful services, you have to be very careful that the changes that you're making aren't going to corrupt that state. And the way that we do it at Netflix is we actually, for every change of a data store AMI, we actually spin that up in a real multi-region cluster, typically 6 to 12 nodes. And we send real traffic at it with a tool called NDBench, which is a benchmarking tool that Netflix open sourced. And what that does is it allows us to exercise failure modes with real traffic load and then ensure that we're still meeting our SLOs and our SLAs. And that's the last stage. So we deploy and we test incrementally, kind of taking incremental risk with our stateful service, starting out in our test environment, moving out piece by piece to production. And the reason why I wanted to call this out is because we spend a lot of time at Netflix when we manage stateful services, making sure that we're not corrupting our users' data. And I think that that is one of the reasons that we've been able to do it so successfully in the cloud, is that we have these pipelines and we've built this infrastructure. All right, so let's get down to the strategies. So the first strategy for managing instances is to actually just mutate the instances in place. So all of those things which aren't the state, we can just change without replacing the instance. And in order to do that, we have to be cognizant of what we're doing. So we have to make these mutations safe. There are lots of ways to do this. One commonly used way in industry is configuration management. Puppet, Chef, these tools work. They work really well. And they're industry standard. At Netflix, we take a different route. We mostly do package upgrades because, in our opinion, Debian packages and upgrading Debian packages is a very tried and true technique. And one thing that we're starting to do more and more is actually using containers to kind of divvy up that stateful instance into smaller stateless ones that we can then replace as a unit. Containers are obviously less mature than than configuration management or package upgrades, but we believe that it's safer because you're actually replacing whole components at once rather than putting your instance in maybe an untested state. Why do we do this? Why do we mutate? One word, it's because of speed. Mutation of stateful instances is extremely fast. We can upgrade our data stores in about an hour. We can make configuration changes, things like changing a YAML setting or a syscontrol in a few seconds. We can upgrade the operating system with a reboot in 15 minutes. And we can do background process upgrades, things like sidecars or metrics sidecars, 30 seconds. So super fast. This means that our changes to do a whole cluster might take days. Rather than maybe rather than maybe weeks or months if we actually had to move the state around. But there's one type of change that we can't solve with mutations, and that's when we want to change the hardware. So if we want to change from I2s to I3s, or I3s to M5Ds, or M5Ds to Z1Ds, you get the idea. We can't do that with mutation because we can't just reboot the hardware into a different configuration. So that's a serious drawback. And at the end of the day, mutations make up many of the ways that Netflix deploys software to stateful instances. It's super easy, it's fast, it's tried and true. One thing is that if you try to concentrate on making it safe, it can be pretty safe. That being said, it completely violates the AMI as a source of truth. And this is a big problem for us at Netflix because we try to align more or less on the idea that the AMI is the source of truth and that we don't have random point mutations and transitions and states that are untested. And we've actually run into this where we end up with fleet drift, where some part of the database is running one version and some part's running a different version, and then somebody makes an assumption, and before you know it, you've caused an outage or worse, corrupted data. So this can be problematic, but that doesn't mean that we don't use it. Now for the rest of the talk, I'll be kind of building into these columns. So strategy 0 we talked about. Netflix absolutely uses those, EBS, RDS, DynamoDB, S3. We make very heavy use of them. But when we do run our databases, almost all of our data stores are stateful instances. We allow mutations on them for the reason of speed. But there are other ways to manage state as well. So the second strategy I want to talk about is migrating state with your clients. So if you have a client of your stateful service, you can move state using that client. So in this example, we've got a service, micro, macro, I don't really care. It's a service that's sending data to a in-memory cache, in this case EV cache, running an old AMI, so AMI XYZ. And we would like to upgrade it to AMI ABC. In order to do that, we follow a simple 5-step process. Step 1 is we mirror writes between the old cache and the new one. Then we wait. Caches hopefully have a reasonable TTL on them. We wait for the TTL, and then at that point, the data set in the new cluster should match the data set in the old cluster. At that point, we can start failing reads over. So I put a little asterisk here because in practice, we don't do this, but I really wish we did. Which is you can read from the old cluster as the source of truth, and then you can check it against the content of the new cluster, and then make sure they match. In practice, what we do is we fetch from the new cluster, and then if we have a miss, we read from the old cluster. Finally, once we're happy with the consistency of the data store, we live launch reads from the new cluster running the new AMI, and then at that point, we're done. We can retire the old cluster. This is something that the cloud makes very easy, because we can just make a new cache cluster, move writes over, and then tear down the old one. Something that's very unique to cloud infrastructures. So migrating state at the client, compared to, for example, mutations, has some pros and cons. One of the pros is that it's relatively easy to do, and it works well for ephemeral data stores, so things like caches, search engines, logs, Kafka, Elasticsearch, Memcache. But it has some cons too, which is, and some of you might have noticed, it's not 100% consistent. What happens if an operation succeeds on one side but not on the other? well, then you have a little bit of inconsistency. And for caches, search engines, and logs, this maybe isn't the biggest deal, but it's hard to use it for ephemeral data, or sorry, for non-ephemeral data, things like persistent caches, which is maybe an oxymoronic term. But I'm curious, how many of you guys have caches where if the cache failed, your application would fail? A good number of you. I mean, it's absolutely true at Netflix as well. I call those persistent caches because if you lose that state, then your databases are going to have a bad day. And you can't really use this technique for that. Instead, what we have to do is the next strategy. All right, you also can't use it, obviously, for sources of truth, things like your source of truth data store, be it a MySQL database or Cassandra database. And this is legitimately more difficult than just like upgrading a Debian package. So Netflix uses client state mutation for client-mediated mutation for mostly ephemeral data, things like caches, search engines, and logs. But we typically don't use it for backwards compatible sources of truth. All right, so the final strategy that I want to talk about is migrating state at the server. So we've talked about just changing the instances as they are. We've talked about having your clients move the data for you. The final strategy I want to talk about is just taking the state from one set of servers and putting it on the other ones. In order to do that, I want to walk through a similar example where we've got a service talking to a data store, in this case, a Cassandra cluster running AMI XYZ. And the first thing we do is we use the capabilities of the cloud to just launch a whole mirror set of nodes. So in this case, we have 3 nodes in the old cluster, node 1, node 2, and node 3. We launched 3 buddy nodes, node 1 prime, 2 prime, and 3 prime, and they're crucially running the new AMI. And now we just kind of go through a kind of choreographed dance. So we start by partitioning the app from node 1. A very effective way to partition an app from a data store is to just stop the data store. And we move state from node 1 to node 1 prime as fast as we humanly can. And after we've done that, we can now promote node 1 prime into the cluster. And it can start taking reads and writes from the service. And in the background, we run consistency repair to make sure that any writes that may have happened in the meantime are repaired. Typically, any distributed database which supports having a node fail will do this automatically for you. Because if nodes are failing, then they can stop, start, and then repair themselves. And then we simply repeat this process. So we can do this one by one, node 1, then node 2. And at the end of the day, we're going to end up with 3 nodes which are running the new AMI, have all of the state from the old nodes, and are completely consistent. So that's the final step. We just kind of do a final consistency repair. This strategy very much relies on your data store allowing single node failures. And an important thing to note here is that we're very heavily leaning on our data store to ensure data fidelity. So for example, Cassandra and other scale-out data stores are kind of built for this type of operation. But almost any data store can work in this way. So migrating state of the server is pretty great because it works for any distributed database. It exploits the concept that a single node can fail at any time. And one thing that we really like at Netflix is that this exercises total chaos on your clients because the IPs are changing, the nodes are moving around, you're restarting your database. How many of you guys out there have heard, we can't restart the database? If we do that, latencies will go up. Nobody? Okay, a couple people. I hear that all the time. We can't restart the database. Well, a good way to make sure that you can restart the database is to restart your stateful services all the time when you're doing your upgrades. But on the drawback side, this system is pretty complicated. It requires complex orchestration. And like I talked about earlier with those data gravity illustrations, moving state is slow. So moving all of that state from one instance to another takes some time. It's much faster with something like Amazon EBS or where you can just detach the volume from one instance and attach it to the other. But this also presents some performance challenges, not only in terms of how fast you can do it, but you just lost, for example, your OS caches. So by moving from one set of hardware to the other, you've completely lost your OS page cache, which is keeping hot blocks of your frequently accessed data in memory. You've also now moved from old instances which have run for a long time and have demonstrably worked really well to new instances which might have some hardware issues. So you have to think about these performance challenges when you're doing this all the time. And then finally, and this is really important, this type of strategy requires that your data store be backwards compatible, which if any of you guys have worked with like Elasticsearch or Cassandra or other data stores, they're not terribly backwards compatible all the time, which naturally makes this strategy kind of problematic. All right, so to kind of summarize the strategies that we've talked about today, we've started with the option of not managing state. We've then kind of moved through mutating stateful instances to actually moving the state using clients, and we've finished with moving the state using the server. And we mostly use the last technique for our sources of truth, things like Cassandra, things like persistent caches. All right, so now that we kind of understand the high-level ideas, let's dive into some case studies of how we can take these basic ideas and we can really take it to 11. So the first thing that I want to talk about is a problem that we frequently ran into with mutation, which is that there's a lot of risk involved. So in this example, we have one AMI, which is running some standard stuff like metrics, discovery, but some things I want to point out, it's running an older version of a data store, Cassandra 2.1. It's running an older version of an operating system, Ubuntu Trusty. It has some syscontrols, things like, or excuse me, sysfs settings like read ahead set to 128. It's using Upstart for all of its jobs. It's not running fstrim. That was a surprise for us. It's running a certain network TC traffic control queuing discipline, and it's using a deadline IO scheduler. So we want to mutate that instance over to the instance on the right with AMI ABC. And some things that I want to call out are some particularly tricky parts of this mutation. So for example, we're trying to go from one version of a database to another. That's fun. We're trying to go from one version of an init system to another. We're trying to go from Upstart to systemd. We're trying to go from one set of well-tested Ubuntu packages in Trusty to another set of well-tested packages in Xenial. And we're trying to change disk I/O schedulers and network I/O schedulers. So I like to say, like, how even do we do this? Like, each one of these mutations is kind of like special cased. Like, in one case, we're going to go do a syscontrol command. In one case, we're going to go, bring down the database, wait a little bit, bring it back up. In another case, we're going to like maybe uninstall a Debian package, reinstall it. For something like Upstart to systemd, like, I mean, how do you even do that live without removing the instance? Well, some of these are, frankly, impossible to do live without downtime. Things like moving your init process from Upstart to systemd, that's going to require us to reboot the instance at least. Things like upgrading the database, this is pretty scary. And if we're trying to do that mutation along with all the other ones, who knows what could happen. But there might be some easy ones like switching queuing disciplines. That's like an online operation that we can do pretty easily. So what we did at Netflix was we looked at this problem. We said, OK, well, we know that in order to handle the hard problem, so the hard problem is going from like Upstart to systemd or from 2.1 Cassandra to 3.0 Cassandra, we're going to have to reboot the instance. And so what we did was we designed a way of rebooting the instance where you would start running AMI XYZ, and then after a reboot, you would be running the new AMI. And let me explain how that works. So it's a simple 3-step process. How many of you guys are familiar with live CDs? Yeah. We essentially built a live CD for our AWS stateful instances. And the way that this works is we look up some metadata, like which AMI would we like to run, in this case, ABC. We write that into a little in-memory bootloader. And then we reboot the the AWS EC2 instance into an in-memory imager, which essentially is a live CD. That goes to S3, gets the root volume for that AMI, and just blasts it onto the root volume. Then followed with a second reboot. Now our instance is running the new AMI, ABC. It loads its data, starts the database, and we're good to go. So we've been using the AMI live upgrade technique to take our stateful instances where we don't want to lose the ephemeral drives and safely move from one tested AMI to another. And this is really great because we only ever run tested AMIs that have gone through that pipeline that I talked about earlier. There's no like partial states where like we're sort of kinda in AMI ABC and sort of kinda in AMI XYZ. We're either running one known state or another. There's no data transfer, there's no IP change, which means that the probability of corrupting data is very low. And this can be done remarkably fast. So in production, we can live upgrade AMIs in about 10 minutes per node. The vast majority of that time is just the time it takes to write data to the root volume. But there are some cons. In particular, there are probably better ways to achieve this goal. So containers are a good way to do that. However, even with containers, you couldn't, for example, change the underlying operating system. We think that the more promising technique is something like active passive flashing, the way that, for example, Chromebooks work, or the way that Core OS upgrades work, where you kind of have two root volumes, and then you can kind of like switch between them. So we think that that's probably maybe the next step of this technique. And it obviously, again, doesn't work for instance type upgrades. We can't magically turn the instance from an I2 to an I3 just by rebooting it. Although Amazon, if you're listening, that'd be pretty cool. And finally, it confuses your security team because all of the metadata about the instance is still saying it's running this old AMI. So like we get lots of notices from our security team being like, hey, you guys are running an AMI from like a year and a half ago. And we're like, no, trust us. It's actually not. So that's kind of confusing. Something like active passive flashing, or if EC2 made this a native product, then we wouldn't have that problem. All right, so AMI live upgrade has been hugely helpful to us to safely make mutations. It's how, for example, Netflix did the Ubuntu Trusty to Ubuntu Xenial upgrade just a few months ago. All right, so the next problem that I want to talk about is when you are moving state around or rebooting your instances for your AMI live upgrade, your OS page cache gets completely eliminated. So the OS page cache is this, it's what most of your memory on an instance is probably being used for when you're running a stateful instance. So in this case, we have a Java program, in this case running Cassandra. It's using 12 gigs of memory on the instance. 100 gigs of memory is being used for the OS page cache, which is caching the most frequently used blocks of your underlying ephemeral drives. And in a healthy state, a database is doing almost all of its operations against blocks of data that are cached in the page cache. Typically, if you're missing the page cache more than like a few percentage, then your performance will be quite poor, and your customers will be sad. So this is a problem, because anytime that you reboot or replace an instance, so using any of the techniques that we're talking about, if you use the AMI upgrade and reboot it, or if you migrate state to new instances, then you're going to lose your cache. And this is really problematic because your very fast P99 latencies now spike, and you might cause an incident. So that's no good. So what can we do about it? Well, it seems pretty straightforward. We can warm the caches. And there's an excellent tool written by a Netflix engineer, Josh Snyder, called Happy Cache, which does exactly this. So when you're running the old AMI, you can dump the metadata about which blocks of files are cached. It relies on the min-core syscall, if you're curious. This happens very fast. It takes about 2 minutes to generate the dump file, which is just metadata. So it doesn't contain any sensitive information. The only thing that it contains is these blocks of these files are hot in OS cache. Then you can reboot, replace to your heart's desire. You then take that Happy Cache dump file, and you put it on the new instance, or in the case of an AMI upgrade, it's already there. All you have to do now is do Happy Cache load, which goes at full bandwidth of your drives, which on modern EC2 instances is exceedingly fast. I think for our i3 8x large instances, we can fully freshen the cache in a few minutes, which is totally worth it because your P99s don't suffer. When you start your data store in step 3, your data store comes up as if it had never gone down. And your clients are never the wiser that under the hood, you've completely replaced the hardware out from underneath them. So this is a crucial tool that we rely heavily on in production to ensure that when we're moving state from one instance to the other, we can do so performantly and quickly. All right, so let's keep going. Let's keep talking about more fun problems. So now we're doing these live AMI upgrades, and we're keeping the caches warm. We're making sure that we don't have any performance impact. And now we hit this really annoying problem, which is that when you're running at scale, the naive algorithm doesn't work so well. So on the left here, you see a 12-node cluster, which if we do one node at a time with a 400 gig data set, it takes about 20 minutes for 400 gigs to transfer with i3 4x larges. So doing one node at a time with this process of replacing instances would take you 4 hours. Not so bad. You start in the morning, go get coffee, take 4-hour coffee break, come back, and you've got new instances. But when you get to higher scales, like maybe 300 nodes across three regions, so 100 nodes per region with 400 gigs, if you just do one node at a time, then it's going to take you 4 days to upgrade that cluster. And this is a problem, because what if the upgrade is crucial to, for example, your streaming working? What if angry Netflixers are at your door because they can't stream? Well, 4 days is a long time to go without Netflix. So this is a problem, and we have to solve it. So how do we solve it? Well, the cloud makes it pretty easy because you can exploit massive parallelism. So at Netflix, we back up our databases. We even restore them sometimes. And it turns out that the ability to restore your database can be really helpful when you want to migrate state from one to another. So if instead of taking one node at a time and following that algorithm of like take the node out, move the state, put it back, if instead we could say, hey, we have the entire data set in S3 as of like a minute ago, because we're doing continuous backups. So we can just spin up 300 nodes and have them all pull down their backups from like 5 minutes ago. And if you write this system properly, you can get the entire data set of any scaled data store restored in about the time it takes to do one node in the old system. So that's where this 20-minute comes in. So the time to replace these instances now takes about 7 minutes per node just to kind of restart the database, plus 20 minutes for the initial download. And this is amazing because it means that you are going to go from those 4 days to a few hours, or if you push the parallelism all the way. So hopefully, if you're deploying a distributed database into Amazon, you have availability zone tolerance. Hopefully, you can deal with one AZ failing. Well, a good way to make sure that you can deal with one AZ failing is to take the entire AZ down when you're replacing it with a new set of hardware. So if you do entire AZs at once, which maybe, your mileage may vary. But if you take down an entire AZs at once using this process, you can replace a data store that used to take 4 days in about 50 minutes. So that's even better than the naive algorithm on the 12-node cluster. And one of the nice things about this type of algorithm is that it scales kind of sublinearly in the sense of because you're doing all of the data recovery in parallel all at once, you don't have to kind of pay that cost for each node. So yeah, with this kind of simple realization that we've got our data store backups and we can use them, you can have multiple orders of magnitude faster upgrades of your stateful instances. And the cloud very uniquely enables this because Amazon S3 is one of the most impressive stateful systems ever. I've seen it do absolutely insane bandwidth to EC2. All right. But let's say you start doing this and everything's wonderful, and then you run into this somewhat frustrating problem, which is that you can download all that data and you can throw it on your hard drives, but do you actually know that that data is the data that was on the old instance? Well, the only way to know is to check. And here I've kind of put together a little bit of an example where we have a node with 800 gigabytes of data. You can see that mostly it's one large file, although most of the files are small. And we're just trying to get a checksum of all the data. So if you just kind of naively parallelize on files, here sprinkle a little bit of xargs on there, and you can hash all your data in 1 hour and 22 minutes. Well, that's really slow, especially if we're trying to replace our instances in a few minutes. Well, if each one takes 1 hour and 22 minutes to verify, we're going to be around here all year waiting for our data to verify. So how do you solve this problem? Well, historically, we've solved this problem by just not checking. But we decided that that was a bad idea. So now we check. And in order to solve the problem, we started with, well, what is the problem? So I went and I ran htop. This is what I saw. Can anybody identify what resource we are running out of? Yeah, we're running out of CPU. SHA-256 is a CPU-intensive hash function, and in fact, most cryptographic hash functions are going to be quite slow. We can confirm the suspicion that it's CPU-bound and not anything else bound by looking at the drives. So here, I'm running an iostat command, which shows us what kind of throughput we're getting. i3 NVMe drives should be able to get a lot more throughput than this. This is pitiful. 400 megabytes per second when we're running all 16 cores. Like, come on, we're going to be here all week. Like, this is not good. And then when we're reduced to a single core, SHA-256 is only able to get 166 megabytes per second, which if you have 800 gigabytes of data, like, this is going to take hours. This is no good. So the solution to this might seem pretty straightforward. The solution is to use a better hashing function. So there's a great hash written by Jan Collette. He's also the author of the LZ4 compression algorithm called XXHash. And with XXHash, using the same naive parallelization, instead of an hour and 20 minutes, hashing all that data takes 12 minutes. And the reason that it's so much faster is because XXHash can actually push an EC2 instance to its disk throughput limit. As opposed to being limited by CPU, now we're limited by the NVMe drives, which amazingly on an i3-4X large is pushing 4 gigabytes per second. Which means that if we do a little bit of intelligence on, instead of just doing a find pipe to xargs, if we do like a little bit of intelligence with like using a little bit of a Merkle tree, we can hash that 800 gigs in about 4 minutes, because we can get 4 gigabytes per second the entire time. This benchmark was kind of throttled by that single process hashing that single file, whereas if we split that file up and then hash each one in parallel and then combine it into a resulting hash, then we can get that 4 gigabytes per second the whole time. And by the way, it's not a typo. That is gigabytes per second, not gigabits. NVMe drives are so amazingly fast that it's almost never your bottleneck these days. All right, so we've gone through a couple of examples of how we can get order of magnitude improvements with like relatively minor changes. I just want to wrap up by kind of going back to the overview of the talk. So we have many strategies, and each one of these strategies we can apply relatively simple, straightforward optimizations to take them from something that might take months or weeks to something that takes a few minutes. And just to reiterate, not managing state is, again, a very viable option. It's often the right choice, especially if you don't have the engineering resources to devote to some of these systems. But if you do want to manage state, then you have 3 main options. You can mutate it. If you mutate it, make sure you make it safe. Make sure that you avoid drift. Otherwise, you're going to have a very bad outage on your hand. If you need to actually migrate the state from one set of hardware to the other, you can do it with clients. The only thing to be wary of here is, of course, consistency. And coordinating with your clients is going to be the key. And then finally, you can migrate state using the server. This is by far the safest option, but it also takes a little bit of trickery in order to make it quick to do and performant for your clients. So with that, thank you guys very much. I'd be happy to take any questions down here at the end or outside afterwards.